Swayam Prabha. Digital India. Educated India.
So, yeah, Amit has asked for a steel example. I don't know how he read my mind. That we'll get into that very soon. But before we get into that, I just wanted to give some related to reinforced concrete. There are a couple of different terms. Oh, mute. Okay, it's unmuted. So there are a few terms that that is used in this area. So let's say you have a reinforced concrete section like this, and you have a blast pressure coming up this way, and you have your reinforcement either down the middle or wherever. So this is your reinforcement. So the terms you'll hear, so if you look at the, let's say, the boundary conditions, simply supported conditions, and then your deflection diagram, and we know that the theta, assuming that's your delta max there. So this is, in reinforced concrete we've seen why theta is often used. It's hard to define the peak delta. So delta is hard to define in RC. So this is RC because of three different concepts. One is what is known as spalling. The second is breaching. So because of these two, and then the third word you would hear is scabbing. To me, again, when I started looking at this, they all sounded the same, and I had no idea of what the distinction is. They all seemed to do what exactly a reinforced concrete element experiences with its breakup. But technically the differences are, the phenomenon of spalling is you have the element depth h, and there is the compression, the pressure here, and so within this element there is a compression waveform. So there is a compression tension waveform propagating through the, so when you are studying the mechanisms through the RC element. So when you study the mechanisms, you would be measuring the waveform within the element, and what this does is, in the back side there is failure in tension due to the reflection causes, and again the combination of the two, it results in tension cracks due to the tension waves. So this is what is called as spalling. Breaching is exactly the same. Now, so spalling, you can see these are chunks of concrete that what you call spall off. So these are not your flexural tensile cracks. Then when you look at breaching, breaching is a more severe form of spalling. So when you have breaching is when you have loss of material So, this part is lost due to damage or due to cracking and spalling. That is breaching when this depth H1, this is H1 is greater than or equal to H by 2, then you say the concrete has breached. So, the RC element has breached. And finally, you have the third one is scabbing. Now, scabbing, now you see why you can't define H, the delta, because the difficulty, where I wrote that somewhere, it is hard to define, it is because of primarily these two, breaching and spalling. I mean, where are you going to measure the delta from? Is it the center or is it the end? I mean, so those measurement aspects are going to be different. Scabbing is considered basically when the failure is defined, you can, if you are able to measure the support rotation, quite often the support integrity is better, is I should say qualified, but you can say it is maintained. The tension and anyway the moments are very close to 0 there if it is simply supported. So, the possibility, and it is also well supported. So, the wave propagation within that is likely to be dissipated better. So, given all of that, if theta is greater than 4 degrees, then you can scabbing. So, this is basically a failure due to flexure. Now, spalling, and let me come back here. We can say that there is again an old research from I think it is Wally, can provide the reference. This is from 1978. Not a whole lot of people keep working on this, measuring this or keeping that as an objective to define these things. So, somebody once does a research and it generally tends to continue as the quoted research. So, if H by cube root of W is, this is in kg per kg meter units, is greater than or equal to Z power minus 0.62. So, H by W power 1 by 3, that is greater than or equal to So, there is 0.07 Z power minus 0.62, then you say there is no spalling if this condition is maintained. And then for this condition, if H by W power 1 by 3 is greater than 0.03, that number goes down, same, this is minus 0.62, then again no scabbing, this is not yes or no answer, no, you can say expected scabbing, again no expected spalling. So, these are some guidelines if you are interested that you can use. So, we'll, what's that? Breaching, sorry, you are right. I think I wrote breaching, right? That is a joke. I can correct myself with no trace. So, no breaching, you are right, thank you. So, examples we'll continue some equivalent SDOF and examples. Again, both are relatively simple, and two things I'd like to do today is one, a steel member example. I'll take up a masonry example likely tomorrow. We'll do an internal vent and an internal room blast. We'll do an example on that. I'll show you. We haven't derived pressures and other such things due to internal. I had mentioned about it a while ago, last week, and talked about a lot of UFC graphs being there. We'll use a couple of them for a simple example, and you can gives you ideas of how to go about doing that. And then so today the plan is introduction to design, and we'll take up potentially an impulse based design, and depending on, I think we should have the time, at least introduction to the what is known as in seismic design. You have various factors. It's called a response modification factor, but does anybody know what it is? Anybody's heard of it? Well, if you can think about it, you don't have to Google or anything meanwhile. Well, it's a seismic principle, but it is not really a response modification factor. I'll talk about that, so you have to be careful when they use it. It's used in a similar fashion mathematically, but not from a physical equivalence perspective. You could say in some ways it is. There are similarities, but in steel and in seismic design, response modification factors are used for ductility purposes, but here it is used for design purposes. So that's the plan, and we'll continue with some examples on this tomorrow. So let's take up the first example in steel. So you have a okay, well, so steel design example. We'll go to the next page. Oh. So we have a single story, many industrial facilities, steel frame building. And here we have just one bay. Clearly you can extend it to any number of bays. Again, a fairly straightforward example similar to what we did, so it will be a good review also. But you can compare some numbers as we look at different. So that's the other objective, is for different types of structures, what kind of numbers we get. Yesterday was an RC. I wanted to mention, can somebody remind me that I want to talk about, I didn't mention that as a topic. If I don't talk about it, something about steel, concrete roof slabs, roof girders. If you just remind me, I'll mention some things. Time permitting, I'll do some examples, but I want to mention something different about them. So I thought of starting with it, but since we have already started here. So let's say this is your steel. Quite mostly you will have simply supported or pinned foundations. You could do fixed foundations, but then that really involves a lot of additional detailing and transfer of moments to the foundations makes it quite challenging. It's not as simple as RC in terms of detailing and construction. So most often you will find simple foundations that are easy to design. So you have here, this is your curtain wall. So this is the wall resisting PR. Oh, how do I go back? Okay, I don't know what I did, but it worked. But I lost something. So you can imagine, so this is the curtain wall, and the height here is 12 feet, and so this is 20 feet, and you don't need the bay. The bay is here, this is 40 feet. So the frame itself is supporting a roof and a dead load. This is dead load, and it is given that the W of dead load, let me make sure it's in one column or two columns. So the weight on one column is 180 kips. So the dead load per column is 180 kips. The section itself is a W24 by 55. Basically, if it's an I section, the moment of inertia for an I, it's a W24, so basically it is 24 inches deep approximately. That's nominal, could be plus minus, and again here the last term is 55 pounds per foot. So IXX is 1350 inches per 4, and you also have ZX. Do you know what ZX is? I don't know if the term is different here. It is the plastic section modulus. The elastic section modulus is I by C, but this is the section modulus. And the self weight, of course, is 55 pounds per foot. It's given that the data further gives you that PR is 5 psi, TD is 20 milliseconds, and this is a triangular loading, equivalent triangular loading. And the question is to determine the peak deflection due to the blast load. So we start with, so this is where some uncertainties come into play. So first step is your structural and dynamic properties, because a column is a little different. It's not the beam supporting the self weight. Let me try sitting in. I don't know if this works today. So is that okay? Fine. So, the structural dynamic properties, we start with the mass of the column, and here the mass in a beam we saw that we could take the slab weight directly. So, in the mass of the columns you can look at considering the dead load from the supported slab. You cannot ignore that. You can say on the one extreme, if it doesn't, you can try what is the response without that, but consider the mass from the dead load and you can take factor of 1. Load factor basically is 1. So, the mass now comes to 180, it skips, so 180,000 pounds plus you have, sorry, this was, yeah, that is what I was trying to see. This is 180 kips total. So, this would be 180 total, plus you have 2 columns. So, 2 times 55 pounds per foot. Remember that here you are using, both columns are working together. So, you have a system which is something like this is rigid and your system is working to deflect. So, both columns, although the pressure is coming on one side, as far as the structure is concerned, that is another decision you make, whether it is, you can do couple of different things. Sometimes in elemental design, if you are designing the cladding, then you are just considering the total pressure and that element alone. Here the whole structure comes into play. So, that is why we are going to take the entire and take 2 times 55, and so this is 12 feet and then divided by 386.1 inches per second square. So, comes to 4.69 pound. Then we calculate the load mass factor, which is and from what we presented yesterday, if you have seen for a simply supported beam with a distributed load in this manner, here the load is still distributed. There are 2 options, you had the elastic and the plastic, and KLM was, elastic was 0.78, the plastic is 0.66. So, the average KLM is equal to 0.72, and I have given you number of other scenarios, especially if it were fixed and it is fixed at the top but moving, then the case is going to be a little different. Then you will have to make some approximations, but all of them come from Biggs, bless you. Now, or you could say it is plastic, and because it is going to the extreme, KLM is equal to 0.66. So, either option is your choice. So, let us go with this value here. Steel especially, in concrete you still have some cracked concrete which is elastic behavior grows. So, your properties that you use are still elastic properties to some extent, but here steel does get into full plasticity, and then your I values then change to plastic section modulus, and so the behavior changes. So, for steel you can go with this value. So, use M is equal to 0.66 multiplied by 4.69, which is, no, this is not 4.69, this is 469, sorry. That's why, you know, I mentioned that there's somebody in my class usually who's got, moment it comes in, you'll have a calculator, he or she will have it ready. So 469, which is very helpful though. So 469, this is 310 pounds. And then, so now the stiffness, yesterday we remember the stiffnesses were of the order of, what are the numbers yesterday in reinforced concrete? Something. So of the order of 10, 20s, 30s. So let's look at what this allows. This gives stiffness of the structure. So this will also, these numbers help you decide later on what type of structure you would like to choose, what type of material you would like to choose for such applications. So here it is a rigid, so this part is rigid and this is fixed. Oh sorry, that is not needed. So you have this column here, and you could, there are two options. You could look at it this way, or then you will have to look at it from this perspective, where you have, you're allowing a little delta. But let's start with a simply supported assumption. You can modify to this assumption if delta is large, or very large I should say. If it is in the order of several inches, 10, 6, 7, 8, 10 inches, then you should look into it. But let's start with this assumption, and for this simply supported assumption, we know K is equal to 384 EI by 5L cubed. So that value comes to 384 multiplied, E is, people use 30 or 29,000, either one is fine, and there are two columns. So 1350, this is 2IX, two columns, and divided by 5 times 12 cubed. So yesterday you saw I was hardly 20, 30, 40, whatever that range is, but now I is extremely high. So you will get these steel stiffnesses tend to be, so just make a note of it, steel structure stiffnesses, it's true for any situation of course, very high. Yesterday the time period was 66 milliseconds. So the fourth characteristic we'll look at calculating Tn, the natural time period. So Tn is 2 pi square root of m e by ke. So here it is 2 pi, me was 3, yeah, this is m by k. So m was 310 and here 2104, so comes to 0.078 seconds. The natural time period, again the load, dominant load was the dead load. Yesterday I don't know if we had this much of a high load, but it still comes to something similar, 28 milliseconds, 78 milliseconds. Then help me with this number please. Yesterday we made that correction, we calculate the static deflection load on the structure. So let us start with that. Here the load on the structure P naught is PR multiplied by the tributary area, and PR is 5 psi. We have 20 feet and the height is 12 feet. So comes to, if I divide it by 1000, it is 172.8 kips. The resistance function, resistance is quite easy to calculate here. So calculate the maximum resistance, and I will mention a couple of things in this case. In which case? For what calculation? I did. So this is the wall, 20 times 12. Yeah, if it is not there, then how is the load even coming, right? There is no load. I mean, the only area that is exposed is the flange. So if it is vented, those are again best estimate or best whatever judgment calculations. If the wall is not there, yes, you won't have that pressure coming in. Now the maximum resistance, I am going to do the simplified version, but in the US, and actually I will make a, this is a little tidbit corresponding to, I am sure you have design, who works in steel design here, anybody? Nobody works in steel design? So at least in undergraduate classes, what's the, you have a, what do you call, special publication, or what do they call that, design aids for steel? Huh? SP6, yes. So just as I was mentioning earlier to Professor Arigappan, so when I was doing my master's first semester, 6 months, my job was to develop SP6 curves, because that time computers were just coming in. The first fax machine was there, including developing the graph sheet using coding, and then all the design equations, and then deciding optimal solutions. So if you see this is exactly what I did for 6 months here, the first SP6, it typically looks something like this. And then if you have a heavier section, it might go something like, if it goes as, oh, I don't know what happens here. Ooh. Undo. What's that? Control and scroll. Yes, this.
Press control.
Control. Oh, scroll there. Ah, I see. Okay. Oh, thank you. Perfect. Okay, let's not worry about that. So if there is a lighter section, then you draw something like this, and then it becomes, so basically solid sections are the most the axes are moment versus the unbraced length. So you have here a beam and you are designing with supports there, that is your L sub B, or it depends on which, all of these are, let us say LB1, LB2, LB3, they are typically equal. This is the unbraced length. You are hopefully familiar with the concept. An unbraced length is you have beams on the other side preventing lateral torsional buckling. So, these prevent lateral torsional buckling. You've heard of that term, right? Lateral torsional buckling. Now, so you have two of them, LB and LR. So, there are given a section, there are tables, say a W24, I do not have those numbers right away, but you can there are equations and there are tables. I think IS 800 should have both of them. So, you have this as so many feet, I am sorry, LP, the plastic length, and then you check if unbraced length is less than LP, then your moment capacity, most of the time you want to design in this region, your moment capacity is nothing but Fy z sub x, and if B, so no LP sorry is, so the unbraced length, this is your unbraced length. If the unbraced length is between these two, it is a linear variation, and then you are given by another equation. Basically, it is a linear expression. We will not spend time on it, do not want to. And then if this is inelastic lateral torsional buckling, and this is plastic section capacity, and then if your LB is greater than LR, then you have elastic lateral torsional buckling expression. So, you have to use Mn from either one of them, and in addition you also have the moment magnification factor. Also you consider a moment magnification factor CB, well, let us call this as needed. But so all this can be incorporated, but let us consider, keep it simple here, consider the case of LB, which is 12 feet, which is supported only at the ends, or if you have other, for example, you have girts, if you have these side beams or girts, these are also called. So, in that case your LB is now 6, and there is a little more to it than just, there are the CB accounts for some things, but for simplicity let us consider LB less than LB, whatever be the case, it does not have to be 12 feet even if it is supported. So, let us consider this case so that we can focus on our topics. So, Mn is Fy times Zx, so which is basically your Fy is 50 ksi, so which is 50 ksi is what you use, 400 and no, not 415, 3 something, right? 350 steel, is that what you use for structural steel here? 350 MPa, 400 MPa. Okay, so 400 MPa, 410. That's reinforced steel. Structural steel is 250. Structural steel is 250. Reinforced steel is higher. So yeah, this is of course more 250 you said, right? So in which case would be 36 ksi, A36 is what we use, but most of our W sections are 50 ksi. So, 50 ksi multiplied by 134, this was your plastic section modulus cubed. So, comes to 667 kip inches. Then, so these are the maximum resistance. So, the resistance now Rm is 8 Mn divided by L, because it is simply supported. So, this is 8 MP divided by L, and that value now is 8 times 667 divided by 12, so comes to 37 kips. So, Rm is and I do not know if we have the. So, the next step, which is 5, so we find or calculate delta static and delta dynamic. Now, yesterday I had mentioned delta static as P naught by K and later corrected to Rm by K, right? Why did I do that? Rm is considered as you're right, maximum. So, basically if the difference was, if this is P versus X or delta, if you consider P naught by K, you might go here, right? P naught by K gives you delta static here. But if your resistance is only restricted, you really cannot go beyond this point. So, this should be your delta static in elastoplastic analysis. And when you did the problem, were you able to compare the two, and are they similar yesterday? They were? Okay. So, now this is for elastic analysis, and we had to lay a basis. Most of your design is elastoplastic anyway. So, the elastic and the plastic parts are different. So, delta static is Rm by Ke, and if you can help me with this number, 37 kips divided by K was 2104, I believe. K was 2104 kips per inch. Point zero something, 0.1 or 0.18 or something like that. 0.012. Okay, and then we'll look at Rm by P naught. So, 37K divided by 172.8 is 0.256. The third is Td by Tn, which is 20 milliseconds divided by 78 milliseconds, which is 0.256. And from the elastoplastic, I do not know if I have a PNG file, charts. let's maybe go down and so this is, yeah, so what was 0.286 RM TD by TN is 0.256 to halfway, and then RM by F naught is 0.256 again, so this is somewhere here, huh? 0.2. So, and RM by F naught is 0.216, okay. So, let us say 0.2 close to. So, if we keep this line up coming to 0.256, we are probably somewhere here. So, where my cursor is, so 1, 2, 3, 4, 5, 6, 6.5 you would say roughly. So, comes to from those charts, the delta dynamic by delta static is say 6.5. So, you can calculate your delta dynamic is 6.5 0.012, 78, so 0.078 inches, is that right? And here for steel, calculate ductility ratio. For concrete we went with theta, but mu max divided by not delta max divided by delta sub E is mu, which is in this case 6.5. It's doing a lot of things on its own today. Okay, let's see. I can't seem to move it back. Oh, there it is. So, and then check the LOP offered. We'll look at that in a couple of minutes. So, any questions? I don't know if this is the type of problem you were expecting. The blast pressures here are more petrochemical type, but of course the TD is lower, but it's still. So, the LOP, for example, insert an image. Let's go to no, not that one. Lecture 6. So, this is response limits, yeah. So, let us open this one and see. So, this is for concrete. So, here you have the LOPs. Superficial is high LOP and this is very low level of protection. So, this is your medium low LOP and medium level of LOP. So, these are for concrete. For concrete, as we have seen, only the superficial is mu max, everything else right from MLOP all the way to high LOP is in terms of theta. Let me see if I have something for steel in a similar way. I might have given it sometime earlier. If not, I will try to find one. And transformation factors, these are dynamic deflection, So I don't seem to have those. I think transformation factors, we have given those 8-page files or several page files yesterday. So let me put these also, table 33A. I'll insert these for reference purposes. We have used it, so let me put those in anyway. So this gives you LOP and damage limits. Can you guess why these numbers in pre-stressed concrete are much lower than reinforced concrete? And again, in reinforced concrete, in compression, so for instance, you have a blast inside a building and then those pressures on columns are basically compressive loads. So flexure, why is this limit high compared to pre-stressed? Let's just look between these two. What's the big reason why the limits, even a 2-degree provides a very high level of protection, whereas very low level of protection. Basically, it's considered beyond that is gone, whereas RC you can go up to 10 degrees and it is considered as failed. Mostly RC damages you can't really predict, and the columns, there is a lot of stiffness in the material, right? Because of the loss of damage, spalling, we talked about breaching, all those things. So as soon as those two effects start coming in, the stiffness drops considerably and the column, there is still integrity, but it deforms a lot. Whereas in pre-stressed concrete, they are designed for elastic behavior. So the effect of spalling and breaching is much lesser. Elements are likely to be deeper, so those effects are minimized a lot more in pre-stressed concrete compared to reinforced concrete. So that's another reason to also consider pre-stressed concrete in these applications, but unless it is really required. The other, I'll just insert them for the sake of completeness. We have this table 3A, I think it's continued. So basically it's the same thing. Continued for masonry. Now structural steel, are you able to read that or it's too small? Wider, right? Oh, the box here? Oh, I see. So the box at the top. Much a little better, right? Okay. So here if you see beam with column with axial failure, it is in terms of mu max. So hazardous conditions, column, it's axial failure. So this is axial, then beam column with compact section, again non-compact section. So in our case, mu for is less, should be less than or equal to 3 for low level of protection. So going from here, you see that it is definitely very, less than or more severe than low level of protection. So basically you would say, you would classify this as a very low level of, if you had this design, you would say this is a very low level of protection. Other tables that would be useful are table 3 3A, I think this is what I there is a table on dynamic factors which I shall send later on for DIFs and SIFs, but for now I'll just refer to it. I don't have it right here. So any questions? Let's do another example. Oh, there's a table 3-4? This one? Yeah, yeah, this is exactly what I was, again for information purposes, can keep this as, if you're going to keep these notes for a while, or I mean it's good to have all this information in one place. So this gives you the various dynamic increase factors for different, the 1.1 that I used for hot rolled steel yield strength and tension compression. So you can use the SIFs and DIFs in this case. So you could see why, maybe one thing I could have done here, for example, deformed reinforcement, while hot rolled flexure is 1.19. So perhaps I am not sure why I did not consider that. I do not know why my notes, I might have missed it, or here I will add a note, consider Fy dynamic is SIF multiplied by DIF multiplied by 50. So from this table here, average strength increase factors, unless yield strength of hot rolled sections is 1.1, and here flexion and shear DIF is 1.19. So you could use here 1.1 times, and I do not know what that comes to. So that change you can make and look at it. I think I should change, for some reason I missed that in my notes. Okay, any questions? Okay, so I've looked at this. And we've also looked at strain rate effects. Okay. Now let's look at the second example. This is an internal room blast. This is a topic we have not covered. So consider an internal room this way. And typically what type of explosive is likely to be used in an internal room? Hand carry, most likely. So this room has, say, dimensions of 30 feet, 30 feet and 15 feet, and it's an explosive right in the middle of 5 pounds, and then it has vented areas. So basically windows, 2 windows and this is considered vented area. Now the windows is also a frangible element, and there are we'll talk about that. I'll bring that into the picture when the graph comes in. So wait. Okay, question is, to given a package bomb at on the floor, you are required to check the roof beam design to withstand the explosion. I'll give you the details of the roof beam. So this is the question, and the roof beam is so you have roof beams and the slab. So here the beams are, so the beam itself is right, again these are all simplified versions. When you do a roof beam, the pressures are going to be upward this way. So you can consider them to be rectangular beams. So here you have two number 7 bars, which is two 7/8 inch diameter bars, and here you have 4 number 6, or this is 3/4 inch. So that's the FC prime and FCK, those are all the standard values. But let's look at first the determination or calculation of the blast pressures. Now what you have is, you have a blast loading in an internal, so you have blast plus you have gas pressures. Due to the build up, there is, like you have equivalent, this is equivalent to the ambient, similar to the ambient dynamic pressure Q naught, and it goes to, so the loading is going to be similar. So determine the blast loading and the gas pressures. It's going to be exactly the same. So let's say this is P versus T. The reflected pressure is PR versus T, and the gas pressures is PG. So this is, let's say, TD, and this is TG. Is it my phone? I was wondering, some noise is coming. I don't know whether it's. Yeah. It opened a shopping ad. And I think there's no idea. There's a store. I didn't do anything, right? I wasn't shopping. You agree with me? You could hear it, right? Something, a voice? No? I could hear it, so I was wondering. So, again, this you can see, we'll start with from the UFC 340-02. We go with figure 2-15. This is surface blast. You get W is 5 pounds, R will be now 15 feet, height of the roof. And from here you calculate your Z. From here you get the following values. PR is 32.8 psi, TD is equal to 2.2 milliseconds, and IR is 36 psi milliseconds. Then to calculate for gas pressures, we'll use a couple of other charts. We first need to calculate the vent areas. This is for the doors and windows. So here assume AV is 500 square feet given. If not, you can calculate those areas. Next is you find the free volume of the enclosure. We call that VF. VF in this case, the ceiling height multiplied by the base area, 30 feet by 30 feet. So, this is 13,500. Process again fairly straightforward. Third thing is to calculate the TNT weight by, so this is W is the TNT weight. So, this comes to 5 pounds divided by 13,000. So, this is 3.7 into 10 power minus 4. This is minus 4. Then there are the charts, and let me insert this image. It's the charge weight versus it's a log scale. Oh. Oh, I have to go to the next page, I think, right? Or maybe it will come down. let me keep pulling it down. Okay. So here if you see, this is W by charge weight to free volume ratio. And this is the maximum gas pressure, and what we are getting is 0.00037. So here it is 0.0001, sorry. So we are getting charts 0.00037, our example. So you can use something very close to this one, and so that is 100, this is 10, so maybe 10, if you can extrapolate or you can come down, so maybe this is 20 psi or 25 psi, let's say. And help me with some calculations, my numbers are a little different from, so you agree with me, PG is 25 psi, somewhere there. Or if you assume even 10 psi, I do not know if, since it is off of charts and the lowest value is 10, that is also something, and we get a big difference in the numbers. So either way you can assume the one that you need, and then there is another chart that we use. So here the steps are, now we are finding the scaled impulse. We found this gas pressure, here where we are finding the scaled impulse. To find the scale impulse, so the steps are, first step A is we find the area of the vent divided by Vf in feet cube. So this is Vf power 2/3. So if you see here, this is Vf power 2/3. So we have 500 square feet divided by Vf is 13,000, comes to 0.88, and then the second step here is find the ratio of the weight of the frangible element to the weight of the TNT, of weight of the frangible element, and we have not given this, we have not going deeper into this. So this is the ratio, and it goes from 0 to all the way to 100. So if we assume 0.3, again that is just a random assumption here, but a frangible element is, you might have a catcher in or something that is breaking up in the window. For the, basically you could take the weight of the window versus compared to the weight of TNT, that is also a reasonable assumption. So now use for 0.3 and the number is 0.88, so let us say somewhere here, or 0.9, and 0.3, the number comes to about 100 or roughly that's 200. So it's a little bit, it's right down the middle. Let's say 150 psi. 150 psi milliseconds. So what we get is PR is 32.8 psi, PG it could be 25 psi, and I don't know, there is also, and then your I gas is 100 and what did we say, it is 150 psi. So excuse me. So Tg is 2Ig divided by Pg, so 2 times 150 divided by, if you do, I think let's go with 10 because it's way off the charts. So use this for Pg. So if I do divided by 10, this comes to 300 by 10 is basically 30 milliseconds. Did we get the scaled impulse correct? No, 100. Yeah, it seems right. About 150 seems right. What's that? So, yeah, PSI, this is for the, so this is the scaled, the scaled gas impulse. So this is PSI milliseconds by, W power 1 over 3, you're right. So here you have, so Ig, this is what this is by W, right? So you get your Ig is equal to, you can hear 150 psi multiplied by the 5 multiplied by W power 1 over 3. How much is this one? 256. Thank you for the correction. So from here I can get Tg is 2 times Ig divided by Pg. So 2 times, again please help me with this, by 10 comes to 51 milliseconds. So your final expressions for the gas pressures would be, or for both together, P versus T, you have the, what was TD? 2.2 milliseconds. So the duration is very low. So let's do a cut out here, and then this is 32.8 and this is 10, and this value here is 51 milliseconds. So that's your gas pressure diagrams. Then step 2, once you calculate that, the process is similar. We calculate the member resistance, and now we are looking at the compression block at the bottom. You can do either a doubly reinforced design or you can do a singly reinforced design. So let's consider here, we'll ignore the compression block reinforcement. Again, you can get fancy and definitely do all of that, but we'll keep it simple here. These are 4 number 6 bars given. This effective depth I have not given you, but the effective depth is 16 inches. The width of the roof beam is 6 inches. So we calculate A, the depth of the compression block, as AS top Fy dynamic divided, the factors we use are 1.85 Fc prime dynamic multiplied by B. So 4 number 6 bars is 4 times the area. It's not exactly the area after number 9, but for now this one works. So this is 1.76, then Fc prime dynamic is I thought I had this calculated somewhere. Anyway, we have seen this yesterday. So Fc prime dynamic was 5.24 KSI. See yesterday's notes. And Fy dynamic was 77. So from here you get A and B is equal to 6 inches. So we have all of these. So A comes to 1.7 inches. The moment resistance is again AS top Fy dynamic multiplied by D minus A by 2, and we so know all these numbers: 1.76, 77.2, 16, and A is there. So the moment resistance comes to 2059 kip inches, and Rm is 8 Mn by L, which is 8 times 2059, and the span was 30 feet, 45.8 kips. We'll finish this and then another 5-10 minutes. Then the last step is, or the couple more steps, is check the blast force Here you could do a couple of things. You could input into nonlin the curve and find several things. You could find delta dynamic, you could find mu, you could find the reaction, the response versus time, force, the response force versus time history, all these things you can find from there. So here you have, but let us do some hand calculations just to complete this. So the tributary area is, assume that the roof is, this is and the span is 30 feet. So this way it is 30 feet. So assume that the tributary area responsible half to half, this is 6 feet. So tributary area is 6 feet. So the force F naught you can consider to be the, here you can calculate the total is here 32.8 and 10, the gas pressures. F naught is due to Pg and P blast independently. They both occur at the same time. There it is, although I have plotted in the same graph, they are occurring independently of the same time. So the total P is PR plus Pg. The duration of the blast is 2.2 milliseconds. The peak is also occurring. Of course, it does travel. So for design purposes, it's going to be a little lower than that. We really don't know how to estimate it. So this we can say 10 plus 30, or the other way around, is 42.8 psi. So note, even a hand bomb 5 pounds, range 15 feet produces, this is fairly high. 42.8 is a high number, but your impulse is not that high. Your impulse is, what did we calculate, 256. It's, well, I wouldn't say it is low, but 256 is also about a medium range impulse. So this is high pressure and a medium range impulse. So now the total force P F naught is 42.8 psi multiplied by the tributary area 6 feet multiplied by the span, so divided by 1000 comes to, so it's quite high. Then I'll use some predetermined numbers for this case. You know, we have gone through an exercise of how to do this. Calculate SDOF parameters. I average is 5,500 inches per 4. The K is given to be 33.1 kips per inch. The mass is given to be 27. So these are all given. You can calculate them also. And so Tn comes to you can take mass effective, the KLM, to be 0.72. So this comes to 0.158 seconds, or then find delta dynamic as we have done before. TD by TN is going to be very low. This is 2.2 milliseconds, this is 158 milliseconds, and this is an extremely low number. So if you go to, that's not even TD, yes, still consider TD. So the question comes is which one to consider, right? Now you have gas pressures. So there is, so usage of the elastoplastic response spectrum is questionable, is used with caution, let's say. The best would be use nonlinear. Here best option is use nonlinear. Maybe we can try this. Why don't we can try this for the tutorial, right? Let's try this problem with the tutorial, and we'll even compare it. But the thing to keep in mind, what I wanted to mention is you have these beams and then the pressure acting from the bottom. You can get the reaction force. This is the reaction as a function of time. I think so. You can get the force from your SDOF as a function of time. That's your spring force, and you can consider. We have taken half of that. If you do, is your reaction force, right? You have two reactions. So from nonlinear, the force as a function of time, whatever it gives, this is the reaction force for the entire system. So you can divide by 2, say maybe half of this value. Or this is your response. This is a force in kips per second. Your dynamic shears, you can combine them. These are, I don't think these are exercises we will take. And as we have seen yesterday, this is V of t is a coefficient. This is a dynamic shear force factor plus this is R as a function of time plus 0.115 multiplied by the force, applied force then take the maximum value. and then you get, so you as I had mentioned, there are other programs that gives you dynamic shear as a function of time. Nonlinear quite doesn't give you that, because you're plotting your PR and PG as a function of time, but you're not plotting this, you can't, it doesn't add those up. So you can develop your own Excel sheets, you can output and then add force as a function of time, add both of them and see what you get. So that's basically what member analysis is. We've done a slightly different problem for internal gas. Main thing to note here is the addition of those pressures. And then, so a brief summary as we leave. Might see if I can get another example done depending on the time. We do have some time. So just as a summary, I always like to summarize. So first step is to calculate the blast loading. Then compute the member resistance. So the member resistance typically this way or this way, or, but if you do this, you need to know all these points. So typically two of them are used, either this one or this one. Then all you need is this point. Then the third step was to define the SDOF properties. Then fourth was either use nonlinear or hand calcs to find delta max and delta static. And then 5, you find theta and or mu from delta dynamic or delta static. And the 6th was we check the appropriate level of protection provided by the element. The other thing, one other thing let me quickly mention is this: when you are designing, let's say you are designing, this is a girder and this is your, let's say, roof beam. The girder design is based off a reaction. So the girder is not designed for your pressures directly, for the PR, PG, IR, etc. directly. They are designed using the reaction time history, just like the force from nonlinear, let's say. And maybe I'll get into a little bit of that, but just as a overall point, it is designed for the reaction forces directly, because they are already accounted for, and then you can take the max values, or you have to be creative basically in doing something like that. Okay, I think we'll take a break here. This will allow us to move to the next topic, a separate design based topic after that. So, I mean, when there is going to be explosion, there is going to be internal gas generated, right? And that gas is going to give the pressures on the sides. Any explosion has gaseous formation, fairly reactive, highly explosive gas formation. So, just imagine it's like smoke, right? Pressures. That's your gas pressures. What's that? Yeah, exactly. It's equivalent to that. The only thing is we are designing here for the combined effect. There we are designing for the reactive for PR. But here, since the gases explode and it's the distance is short, you can say, okay, after 2.2 milliseconds or whatever, if you can find the gas pressure velocities, and then, but then you're getting into levels of complexity. This is conservative anyway. 32.8 plus 10 is highly conservative. You should, yeah, there is the icon next to that run button, and there you'll see the force versus time, spring force versus time. You can take that to be the reaction force. Okay.